Okay, so with the other speakers, I'd like to thank the organizers for this very nice conference and for inviting me to speak here. So I'm going to talk about some work in progress with Ofer Aharoni, Shlomo Razamat, and Nadi Seiberg. And for motivation, let me just review some basic facts about supersymmetric dualities. So these are obviously very useful probes to get a deeper understanding of quantum field theory and string theory. And so it's very useful to try to gather as many of them as we can and to understand them as well as we can. And in particular for dualities between supersymmetric quantum field theories, there's by now a vast web of such dualities in various numbers of dimensions and with various amounts of supersymmetry. So let me just review a few of them. So first of all, there are exact dualities, which are typically between conformal, superconformal theories. So some examples would be mirror symmetry of 2D Calabi-Yau sigma models, and S-duality of 4D n equals 2 theories, including 4D n equals 4 superangles theory. But then there's also IR dualities, which are dualities between two theories which are not exactly equivalent, and they're not conformal, but rather at low energies they flow to equivalent superconformal fixed points. And there are also many examples of these. So for example, Hori-Vafa duality in 2D between linear sigma models and Landau-Ginzburg models flows to a special case of mirror symmetry. 3D mirror symmetry exchanges the Higgs and Coulomb branches of the IR CFT for certain 3D gauge theories. And Seiberg duality for 4D n equals 1 theories. A typical example is this between SUN QCD with NF fundamental flavors and SUNF minus NC with some additional singlet fields. And there are many examples with different gauge groups and matter content, and also examples in 3 dimensions and 2 dimensions. And there are many other examples. So what evidence do we have for these dualities? So first of all, we can compare the quantum moduli space of vacua. We can match the spectrum of BPS operators and boundary conditions. We can look at 't Hooft anomalies. And we can check that they're consistent under RG flows. So if we start from a duality and we deform them by some relevant operators, we should get to a new duality. And another test that's emerged in the last several years and become very popular has been to compute the supersymmetric partition functions of these theories, which gives a very rich observable, which is RG invariant and therefore duality invariant. And it actually turns out to contain much of this information above. So it's a very powerful test of these dualities. So where do these dualities come from? So there's several places. First of all, there's many string constructions of many of them, where we take some low energy limit of string theory and apply string dualities. And they can also be derived from other QFTs. So for example, S-duality in 4D arises by compactification of the 6D2,0 theory on a Riemann surface. And there are many other examples of this form, as Kumrun discussed in his talk today. And also many 3D n equals 2 dualities can be derived by compactification of 4D n equals 1 dualities, as shown in a paper with the same co-authors a few years ago. So this second method of generating dualities is what I want to talk about today. And so in this talk, I'm going to ask the following 2 questions. First of all, how can we describe the theory that we obtain by compactifying a d-dimensional QFT on S1? Can we find some useful description of it? And second, when we have a d-dimensional duality, when does it imply a duality of the theory we obtain in d-1 dimensions by compactifying? And just as importantly, when does it not apply a duality? So by answering these questions, we can hope to better organize this web of dualities to see which ones are sort of more fundamental and which ones can be derived from them, and also maybe to find some new dualities. So in a little bit more detail, if we start with 2 theories which are exactly equivalent, so conformal dualities, then they're still going to be equivalent when we place them on a circle. And so at low energies, when we look at the effective d-1 dimensional theories, these should be equivalent. And so this is a more or less straightforward way of generating dualities. However, for IR dualities, this is no longer true. So to understand what's going on, we can look at the relevant parameters which initiate the flow from the UV to the dual IR theories And let me define these quantities, which I've multiplied by a suitable power of r so that they're dimensionless, where r is the radius of the circle, and these mu a's are the relevant parameters. So when this dimensionless parameter gamma is very small, then we're effectively reducing the UV description of the d-dimensional theory. And so we have a Lagrangian description available to us, just a naive dimensional reduction of the d-dimensional theory. But there's no reason to expect these d-1 dimensional theories to be equivalent. On the other hand, if we take the gammas to be very large, or equivalently take the radius of the circle to be very large, then we are basically reducing the IR descriptions, and these should be equivalent. However, these are now strongly coupled theories that we're reducing, and so there's no reason to expect that these will have some kind of useful Lagrangian description. So the goal will be to somehow reconcile this problem, how to make some progress given that these two limits seem to be incompatible. Okay, so in more detail, what I'm going to focus on in this talk is the case of 3D n equals to 2 theories, in particular 3D n equals 2 gauge theories. And here there are two types of relevant parameters that are going to arise. So there's gauge couplings, which are relevant in 3 dimensions, and real mass parameters, which are certain supersymmetric mass parameters that we can define associated to the flavor symmetries of a theory. And correspondingly, these dimensionless parameters that are going to characterize the theory on a circle, I'll define gamma j to be the jth gauge coupling times r, and Ta to be the 8th real mass times r. And as we'll see in examples later in the talk, these gammas will basically control the asymptotic behavior of the metric on the target space. Whereas these TAs are going to be Kähler moduli, so they're going to give rise to normalizable deformations of the metric. So another important feature for in 2 dimensions compared to higher dimensions is that whereas in higher dimensions we have a moduli space of vacua, in each vacuum is a superselection sector. In 2 dimensions there is no moduli space because there are no massless scalars. So instead, the ground state of the system is spreads out over the target space, and there's typically a single superselection sector. However, there's exceptions to this. So in a UV theory which has multiple branches, for example, if you look at an n equals 4 gauge theory, which has a Higgs and a Coulomb branch, these branches can, as we undergo RG flow in 2 dimensions, they can develop long throats where they connect, and at infinitely low energies, they can be flowed to decoupled CFTs. And so we can find a direct sum of decoupled CFTs. And this is going to play an important role when we describe the reduction from 3D. Okay, so let me start by considering a very simple example of a free gauge theory. And here there's a abelian gauge field with a Maxwell term, a massless scalar, and a massless complex fermion. And it's convenient to dualize the gauge field into a scalar. So in 3D, electromagnetic duality relates a abelian gauge field to a periodic scalar with the gauge coupling. And when we do this, we find that the moduli space of this theory is a cylinder of radius G3. So now let's try to reduce this theory. So we place it on R2 times S1 with radius R. And the Kähler potential of the scalar picks up an extra factor of r, and so in the 2D fields, in their normalization, the radius of this cylinder is square root of G3 squared times r, which is this parameter I called gamma. But this 3D theory on a circle has an alternative description where we express things in terms of the third component of the gauge field, or in other words, the holonomy along the circle, which becomes a scalar in 2D. And is identified by large gauge transformations, so it's also periodic, but you can work out that its radius is actually 1 over the square root of gamma. So we have these two descriptions that we obtained from 3D, which are equivalent. And so there's 2 lessons that I want to take from this example. First of all, that 3D electromagnetic duality is reducing to T-duality. So these 2 descriptions are T-dual, and this was already shown by Aganagic et al. And maybe more importantly, is that these 2D theories we obtain depend in a crucial way on this parameter gamma. So gamma is a moduli of this CFT, and it has a very important effect. Okay, so now let's go to a more interesting example. So in an interacting gauge theory, so let's look at SQED with one flavor, or in other words, two chirals of charge 1 and -1. And we'll consider at it, you can convince yourself that there's two branches, a Higgs branch where the chirals Q's get VEVs, and a Coulomb branch where sigma gets a VEV. But note that when that happens, the Q's have to vanish, and then in order for this term to vanish, the Fi parameter has to be 0. So this Coulomb branch only arises when we set the Fi parameter to 0, whereas the Higgs branch is always there. So the moduli space of this theory at zeta equals 0 looks something like this. So this is the Higgs branch, and then the Coulomb branch asymptotically looks like a free gauge theory because we've integrated out the matter. It gets a large mass. And so it's asymptotically a cylinder, again, of radius g3. And quantum effects cause it to pinch off where it meets the Higgs branch. So we get a moduli space which looks like this, 3 branches connected at a point. Now, when we flow to low energies, or equivalently take the 3D gauge coupling to infinity, these Coulomb branches open up asymptotically, and now all 3 branches appear symmetrically, and there's a triality symmetry exchanging them. And in fact, this theory has in simple IR dual description as a Wess-Zumino model with superpotential XYZ, so the XYZ theory. So this is a very simple example of an IR duality in 3 dimensions. In fact, it's a very simple example of mirror symmetry. Okay, so now let's try to reduce this theory to 2D and see what we find. So as a first attempt, let's set the Fi parameter to 0 and place the theory on a circle. And what we find is that, again, asymptotically on the Coulomb branch, we find a nonlinear sigma model into a cylinder with radius square root of gamma. So again, this theory, the theory we find depends on gamma in an important way. And in particular, for any finite gamma, this theory has no hope of being equivalent to the XYZ theory, which has branches which are cones. They don't asymptote to cylinders. So nevertheless, we can try to go further. We can try to find some useful 2D description of this theory. So the natural guess is to look at the 2D SQED with one flavor. But if we just by dimensional analysis, if you compare the gauge couplings, you can see that in order to get a finite 2D gauge coupling, we're forced to take gamma to 0, which is infinitely far from the limit which would give us a duality. So again, it seems like we have run into a problem. And 2D SQED is indeed not equivalent to XYZ. You can do other checks of this, and this duality just doesn't work. So something went wrong. In particular, they don't even have the same number of branches. XYZ has 3 branches, whereas this has a Higgs and a Coulomb branch. So these are just not equivalent. So we have to be a little bit more careful. So the problem before, in a sense, was with the Coulomb branch, because we had these asymptotic components which were cylinders and depended on gamma, whereas the Higgs branch was independent of gamma, because it was independent of the gauge coupling. So to try to fix the duality, we can try to lift the Coulomb branch. And the natural way to do that is to turn on an Fi parameter. So let's turn on this dimensionless parameter T, zeta times R, and see what happens. So I claim that what you find then is the 2D SQED theory, but with a non-zero Fi parameter T. Meanwhile, if you do this deformation on the XYZ side, zeta becomes a mass for 2 of the chirals, and they can be integrated out, and we find a single chiral Z, which is just free. And so this leads us to conjecture the following 2D duality. So SQED with non-zero Fi parameter is equivalent to a free chiral multiplet. And this does appear to be a valid 2D duality, at least up to some possibly minor deformations of the asymptotic Kähler potential. But for example, we can check the matching of supersymmetric partition functions in 2 dimensions. For example, the S2 partition function and the elliptic genus. So let me just make a brief aside to make some remarks about these partition functions. So as I said before, these are a very useful tool for checking dualities. And in a little more detail, they're functions of background fields, typically background gauge fields coupled to flavor symmetries, and also geometric parameters of the manifold. And they're given by localization by a finite integral over the BPS configurations. So in order to study this reduction, the the useful partition function to consider is the 3D supersymmetric index, or S2 times S1 partition function. And this depends on the radius tau of the S1. And in the limit where tau goes to 0, we find up to some divergent factor the S2 partition function of a certain 2D theory. And this divergent factor is related to the central charge of this 2D theory, and some additional terms related to these background fields, which I won't mention. But what this means in particular is that if we start from a 3D duality and we take this tau goes to 0 limit, since the 3D duality implies that the indices are the same, we're guaranteed to find that the S2 partition functions have to be the same, up to these factors which we can just strip off. There can be subtleties in this. So for example, if we have a direct sum of theories in 2D, then we'll typically get a sum of terms like this weighted by different factors, and only one of them will be dominant. So we typically only see the contribution from one of these branches. And so that has to be understood to properly take this limit, but that can be done. So the matching of the S2 partition functions is automatic, starting from a 3D duality. However, the elliptic genus, or torus partition function, is defined in 2D by a twist by a left-moving R symmetry. And this has no 3D analog. So the elliptic genus has no uplift to 3D. So once we find some conjectural 2D duality, the elliptic genus provides an independent test, and therefore a strong test that this duality is actually true. Okay. So now let's look for another fix of this SQED to XYZ duality. So another approach is to just lift the moduli space completely. So to mass deform the theory to a discrete set of vacua by turning on some finite masses. And to study this theory, it's useful to consider the effective twisted superpotential of the 3D theory on a circle. And this was used by Aganagic et al. To study a similar problem. And by taking the R goes to 0 limit of this effective twisted superpotential, one finds that in order to get a regular limit, it's necessary to rescale the gauge field, sigma, by a factor of R, and express it in terms of a dimensionless twisted chiral field X. And then we find a Landau-Ginzburg model with the following twisted superpotential. And the claim is that this massive Landau-Ginzburg model is equivalent to the mass-deformed XYZ theory. For example, the twisted chiral rings match, and their S2 partition functions, which can be computed in terms of this information, also match. And this also follows by, again, carefully taking this limit of the 3D index identities. However, it appears that there's no way to consistently take these masses to 0 and get a duality of CFTs in 2D. So this seems to be the best that we can do in this case. Okay, so now I want to move on to a more complicated example. So let's look at a non-abelian theory, UNC with NF flavors. And this theory has a 3D IR dual description due to Aharoni of UNF minus NC with NF flavors and some additional singlet fields. And as before, to avoid the complications with the Coulomb branch, we're going to turn on a non-zero Fi parameter. And after analyzing what happens, you find in 2D the following duality. UNC with NF flavors is dual to UNF minus NC with NF flavors plus mesons. And this duality was found recently by Benini, Park, and Zhao. But here it's important that the Fi parameter is non-zero again. And again, the S2 partition function identities match as they have to, and one can also check that the elliptic genus matches as an independent check. Okay, so next I want to add another complication, which is to turn on a Chern-Simons term. So in 3D we can turn on a supersymmetric Chern-Simons term for the gauge field labeled by an integer k in this case. So now this theory, UNC with NF flavors and Chern-Simons level k, has the following IR dual description due to Givyon and Kutasov, of where the rank of the gauge group depends on is k plus NF minus NC. And it has also some mesons. And naively, the effect of the Chern-Simons term is trivial when we take the theory on a circle, because this integral gets a factor of r from integrating over the third component, and all these fields are being held finite, and this just goes away in the r goes to 0 limit. And if that were true, what it would mean would be we would find in 2D the following duality. UNC with NF flavors goes to UK plus NF minus NC with NF flavors. But here k is now just a free parameter. So this doesn't make any sense. This can't be right. So where did we mess up? So here it's a little bit subtle to see what's happening, and it's easiest to understand it by, again, going to the mass deformed theory. So we turn on generic masses and use the effective twisted superpotential to find the vacua. And I don't have time to go into the technical details of this, but this can be done very precisely. And what one finds is that as we take the radius to 0, these vacua separate into groups, which are a finite distance between the vacua in each group, but they're separated from each other by a distance of order 1 over r. And so when the r goes to 0 limit, we find a direct sum of theories, and then we can take the masses back to 0, and we find a direct sum of CFTs. So the claim is that for this theory, this Chern-Simons matter theory, placing it on a circle, we find in 2D a direct sum of 2D CFTs. And in particular, what we find is UNC with NF flavors plus UNC minus 1 with NF flavors, and so on. And we find a similar direct sum on the dual side. And now this is nicely consistent with the same duality from earlier, where this term is mapping to this term is mapping to this term, and so on. And so we find a term-wise duality for this direct sum. Okay, so let me just mention a couple other examples that one can look at. So first of all, several years ago, this Aganachij paper that I've mentioned a few times looked at the reduction of 3D abelian mirror symmetry, and they showed that it reduces to Hori-Vafa or Hori-Kapustin duality. We also looked at the reduction of this SUN duality of Aharoni and Fleischer, and what you find there is a new duality, which is a generalization of a duality due to Hori and Tang, which relates SUN with fundamental and anti-fundamental matter to SUNF minus NC. So it's another example of a 2D Seiberg type duality. And we can also look at SPN theories with Chern-Simons terms. And here there's an interesting distinction between, so k can be integer or half integer. So if k is half integer, so if 2k is odd, then what one finds is that the Chern-Simons level lifts the Coulomb branch, it lifts the Coulomb branch in 3D, and what we find, and so since we don't have a Coulomb branch, we expect to find a valid duality, and indeed we recover this duality due to Hori. However, when 2k is even, then there's an unlifted Coulomb branch in 2D, and we no longer find a duality of 2D gauge theories. So as always, the S2 partition functions of all these 2D dualities match, in particular in this case where we don't seem to find a duality, but in this case the elliptic genus does not match. So the elliptic genus gives a stronger test that in this case the duality does not pass. So here we do not find a duality. Okay, so let me summarize. So we've seen that there are various subtleties that arise when trying to compactify IR dualities of 3D theories, and in particular because of the dependence of the 2D theory we obtain on the gauge coupling, the naive reduction typically doesn't work, but in various cases there are fixes that we can find. And to study this problem, the effective twisted superpotential and supersymmetric partition functions are very useful tools. And in particular, we've been able to recover several known dualities and find a few new ones. So some open questions would be to better understand the fate of these theories with Coulomb branches. Is there any non-trivial duality or non-trivial information we can extract from them, or are they do we just get nothing in 2D? Also, there are other dualities that one can look at, try to reduce from 3D to 2D. And of course, one could look at reducing between other dimensions. For example, you could find a more interesting story by reducing from 4 to 2, where you have a choice of Riemann surface. And we looked at this with Abhijit and Shlomo in the case of reducing on an S2, but there are still many other examples to look at. And I'll stop there. Thanks.
Question? Yes. Your arguments about the dimensional reduction of the Chern-Simons dualities, the structure of the argument did not use supersymmetry. Is that right? Or at least the structure that gave the suggestion for the two-dimensional duality. So I wanted to ask, whether one could use the same argument for the non-supersymmetric, the conjectured non-supersymmetric Matter-Chern-Simons theories, suggesting a duality between bosons and fermions coupled to gauge fields in two dimensions.
Well, it sort of used duality in the sense that it was important that we knew the metric on the Higgs branch and that that was not corrected. Whereas the metric on the Coulomb branch was corrected, dependent on the gauge coupling. The metric on the Higgs branch is just exact. It's just given by the classical metric. And that's only true for a supersymmetric theory. So I think it would be harder to argue that the reduction, this allowed you to argue that the reduction of the weakly coupled theory is the same as the reduction of the strongly coupled theory. And for a non-supersymmetric duality, I don't think you could argue that.
Thank you.
Yes. I wanted to understand why you claim that the elliptic genus doesn't automatically work. So suppose you start from 4 dimensions and you've already established that the circular reduction gives rise to these 3-dimensional dualities. So now just put the theory on S2 times T2, reduce on S2, and you get the elliptic genus. And you can imagine squashing the S2 so that it would look like, like a long sausage. So you first reduce the 3D, and then you get the elliptic genus. So I'm just saying that take a 4D theory, study the S2 times T2 compactification. The reduction on S2 gives you the elliptic genus. And the S2, the fact that the only thing that's important about the S2 is the topology. The metric doesn't play a role, so you can make it look like a sausage and that's it. So you can use two-step reduction in 2 steps.
Yeah, I mean, I would have thought that you'd want to reduce on T2 to first reduce. If you wanted to recover first reducing to 3D and then to 2D, you would want to reduce on.
I'm saying that nothing depends on this modular. So
yeah.
Once you've established that the 3D dualities follow from 4D, the elliptic genus has to match. Because you can reduce on S2 and then you get the elliptic genus.
It's even the supersymmetry will be different. You will get 2,0 when you reduce on the sphere, on S2.
You get the elliptic genus.
But the elliptic genus involves twisting by symmetry. It's not existing for the symmetry.
Yeah, but you twist. What you get is the 0,2 elliptic genus. So it does.
No, the elliptic genus that you refer to involves a twist by an R symmetry. It does not exist in the 4-dimensional theory. But the question of getting the 2-dimensional elliptic genus cannot be embedded in the problem in 4 dimensions. This is a question that you can only ask if you're done in 2 dimensions.
You get the standard elliptic genus by its reduction.
Yeah, I think Shlomo's point was that when you put the theory on S2, you do a topological twist on the S2, but that breaks half the supersymmetry.
Right, so
So
you get the standard 0,2 elliptic genus, and that has to match.
that has to match, yeah.
He was talking about the 2-2 elliptic
Yeah.
genus.
Yeah, but you wouldn't be able to get the 2-2 theory that you get by reducing on a torus from 4D.
But in addition to that, the 2-2 elliptic genus is not a question that can be embedded in a 4-dimensional problem.
Excuse me, for the 2D SUNC with the NF and NA fundamental, anti-fundamental duality you mentioned, does that work for zero mass or you have to turn on mass deformation?
No, that seems to work for zero mass. In particular, the elliptic genus does match for that duality. I don't think I mentioned it, but it only works for NA sufficiently small that you don't have an anti-baryon branch. So NA less than NC. But with that restriction, it seems to work even for zero mass.
So does that mean NF equal to NA, we cannot find the difference?
Right, for NF equal NA, we don't find a duality.
Yes.
The original motivation of Abenage's paper was they reduced this Albeelian version, equivalent Albeelian version of mirror symmetry from 3D, and they derived the mirror symmetry of toric manifolds. Do you expect something you could say about now Albeelian mirror symmetry in 2 dimension?
Right. Yeah, it would be interesting, but unfortunately, mirror symmetry involves the Coulomb branch in a sort of intrinsic way, and it seems like we have problems when we have a Coulomb branch. The way they get around that in the abelian case is that they're in the abelian mirror symmetry case, there's an all scales duality due to Kapustin and Strassler, and so there, by reducing the all scales duality, you're able to find a duality even for theories with an unlifted Coulomb branch. But there's no version of that for the non-abelian mirror symmetry.
Any other questions? Oh, yes.
So
So the reduction of, for the reduction of the harmonic activity, how do you recover this cluster transformation of the Fi parameter down to 2 dimensions in the process of reduction from 3D? I mean,
How do you recover it? What?
the cluster transformation, like Jimmy, if Fi parameter the nodes go to minus itself,
Mm-hmm.
but if you have neighboring nodes, they go under through some non-trivial transformation.
You might.
So that's what the Benini are.
Yeah, you might be referring to, there's some contact terms that are generated that are some function of the Fi parameter. If that's what you're referring to, then there were some massive fields some singlet fields in 3D that were integrated out when we went to 2D, and they generate an effective twisted superpotential, which gives these contact terms in 2D that Benini et al. Found.
Any more questions? If not, let's thank all the speakers of the session.